Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
It is time for a segment we call Research in Focus. And right now I am joined from Paris, they're in pole position there in France, Dr. Fei Fei Li of the Stanford Vision Lab and Dr. Sebastian Nowozin of Microsoft Research Cambridge, two of the young leaders in the field of computer vision. Dr. Li and Nowozin, thank you and welcome.
Hi, Chris.
Hi, Chris.
Well, how appropriate that our first Research in Focus segment should deal with computer vision. I'd like to start with you, Fei Fei, and ask you to explain what you mean by giving computers visual intelligence.
Well, think about humans. We go around the world and experience the visual world in very vivid and lively ways. We look at objects, we experience the scenery, we understand what's going on, and we navigate and do things in it. This is what we want computers to do. We want the computers to have at least the same level of visual intelligence as humans.
So, Fei Fei, you're trying to build a computer that can mimic human vision?
Yes, at least. Maybe even better.
Wow. Well, Sebastian, what do you see as the biggest challenge in endowing computers with visual intelligence?
Well, think about it like this. If you look at an image you took at your holiday and the image shows certain objects, then it's immediately clear for you how to parse the image, what objects are in the image, how the scene is composed, where the light is coming from, are there people in the image, all these kind of natural questions. And it doesn't take you any effort at all. But if you think about how to make a computer recognize all these objects and recognize the scene, it's quite hard to find the right representation to go from pixels, from single pixel measurements to these high-level semantic quantities that you want to infer. And really, it's about inferring these representations from a lot of training data, a lot of images.
So how then, Sebastian, do we get the machines to that point? I mean, how long will it take for a computer to recognize that my Chevy Nova is the same category of thing as my boss's BMW?
Yeah, well, one thing that has changed in the last few years is that we now have very large data sets available. So that's a big asset. So we can just give the computer access to a large database of images, and we can try to find the consistent appearances. For example, if you want to recognize a car, then we can ask, no matter what brand the car is, no matter what color the car is, no matter where the light is coming from, what stays the same. For example, maybe the wheels look always the same. And we can learn with machine learning models, we can learn to pick up on these statistical coherencies, and we can build models that can pick up on these features and then produce as an output that there is, with so and so much certainty, there is a car found in the image.
So, Fei Fei, I understand that your lab studies human vision in an effort to tackle just this kind of challenge, right?
Yes, we want to study both human vision and computer vision because they look at the same visual world, and the human visual system is what we know in the universe, the best working visual system. So we want to study it so that we can build machines to do the same thing.
So, Fei Fei, how do you train a computer to approximate human visual intelligence?
Well, that's a very good question. So let's take the problem of recognizing a dog. So what did human do? My son is 1 year old, so you show him pictures of dogs, or if you have a live dog to show him, you show him a few times, and the baby learns what the dog looks like, how it moves, maybe its bark, and mostly how what's its shape and color and texture. The same thing goes to computer. You hopefully show pictures of dogs or models of dogs, and the computers register some of the important characteristics of the dogs, the shape, the color, the texture. And after a while, hopefully the computer can learn to abstract and build a good model so that the next time it sees a dog, just like my 1 year old son, it'll say, oh, look, there's a dog.
And obviously these things have to have labels, and I'm told like 14 million labeled objects. I'm assuming humans have to give these the labels. How does that happen?
Well, yeah, like Sebastian just said, the one good thing that has happened in recent years is thanks to a large amount of data and a large amount of crowd engineering efforts, we are able to have these data with labels. And, part of the work in my own lab was putting together a gigantic data set with these labels. And we utilize a lot of internet technology, a lot of crowdsourcing technology. And with this, the computers can have information to be trained on.
So Fei Fei, once you've trained computers to recognize millions of types of objects, it would seem to open up real possibilities for visual searches on the internet.
Absolutely. Visual recognition is at the heart and core of so many important applications, searches being one of them. A big data photo album organization is another one, surveillance, assistive technology for visually impaired, autonomous driving, you name it. So once we have technology up to the scale and up to the accuracy, we can do many things.
Sebastian, shifting back to you, what are some of the practical applications of computer vision that you're working on?
Well, computer vision is becoming more practical in a sense because everybody of us is carrying around devices that can capture visual information like our smartphones. And I've worked on enhancing, for example, the images that you capture with your smartphone. Now, at first sight, enhancing the image would look like quite a different task to computer vision, and it is, because the representation that you extract from computer vision problems is a high-level representation. But on the other hand, if you understand the complexity of the signal of natural images, and you do a good job at that, then you can also do really good practical applications in terms of enhancing the image you capture. For example, you can remove noise from an image, or you can deblur an image. Many images I take with my smartphone are often blurred, especially at night. So I try to address these practical issues as well, but recently I've also worked on gesture recognition. So in particular, using the Kinect sensor that Microsoft has released, gesture recognition is now in many, many living rooms. And so gesture recognition research is also one of my research domains.
Well, good news. You guys are provoking thought. We are getting some questions from our online viewers watching right now. Let's take a few. We've got one right here. Earlier, Professor Andrew Blake talked about computer vision and the idea of the driverless car came up. You mentioned it a minute ago, Fei Fei. What do you think of that possibility? Is it feasible, and when would you be willing to be a passenger in such a vehicle?
Oh, I think very close. Autonomous vehicle using vision technology is something that's upcoming. There is, like Professor Andrew Blake mentioned, Mercedes is rolling out high-end cars that have that technology. I personally would want to sit in that car right now. So this is something we're making tremendous progress.
Got another interesting question here from a viewer who says her mother is legally blind, and they're wondering could your work on computer vision eventually lead to a device that could restore vision to someone like her, and what would you need to do to get to that point?
That's a good question. So what does restoring mean? So to help a visually impaired patients, there are several fronts we need to work on. One is the clinical aspect, which is more outside of the domain of my own knowledge. But to build a machine that can act like some kind of narrator of the visual environment and scenery to help the visually blind, I think that's one of our goals. We're building components that are somewhat already working. For example, reading text, which is a technology called OCR, recognizing faces. These are core technologies for helping visually blind that are actually relatively mature, but we are also working on technologies such as reconstructing the 3D scenery, recognizing generic objects, understanding the movements of objects and other people and items in the scene. So I think one of the exciting goals of computer vision is to help blind people.
All right, Sebastian, I got one for you from our online audience, and this is something I've seen come up a couple of times. This person says, call me paranoid, but I get a little freaked out when I think about all these vision-enabled devices tracking my every movement. So the question is, how do you see the privacy issue playing out?
Well, yeah, if you build devices that understand the user better, that can indeed enable a lot of useful interactions with the device. So in a sense, understanding the human is clearly a benefit in a lot of applications. And I think the benefit far outweighs potential paranoid risks. But we take privacy very seriously. So whenever we collect data from such a new device, and of course there's a legal process involved that ensures that this data is only used according to the legal laws in place in that country. So yeah, I think the benefits far outweigh the risks in understanding users by visual systems.
Another viewer question for you here from somebody who's hoping you can help their confusion. Confused about the way that the Bayesian inference helps with categorizing visual objects, and they're hoping you can explain this as simply as possible.
Right. So Bayesian inference is a fundamental principle of how to do probabilistic reasoning in complex models. And if you set up a model and you do proper probabilistic inference in that model using Bayes' rule, so using the calculus of probability, the calculus of uncertainty, then Bayes' rule will tell you exactly what you need to infer, and it will lead to exactly the conclusions that are encoded within your model. So in that sense, Bayesian inference and the Bayes' rule is enabling inference in probabilistic models. And if you have a model for categorizing images, say, then just applying the Bayes' rule allows you to classify images.
Got a question that just came in here on the surface. It says, what are the computer vision techniques that made it into mainstream consumer technology that made you go, wow?
Well, I just say one word, connect.
Right. I think my daughter would agree with you on that one. I can lose her for hours on that, watching her own avatar explore Disneyland and things like that. So I'm with you on that one. I got another one here from a student. Says, I'm a high school senior. I want to eventually go to grad school and to work on artificial intelligence. Wants to know what kind of courses should they take as an undergrad?
Well, mathematics, for one. So mathematics enables all kinds of statistics, probability, machine learning, and it's really at the core of what we use in machine learning every day. So mathematics and computer science, I think that are the key ingredients you need if you want to do research in artificial intelligence, machine learning, statistics, probability.
Great stuff. Well, you know what? Good timing, because our timing is up. And thanks to both of you, Fei Fei, Sebastian, really illuminating look into how machine learning is teaching computers to see the world the same way we do. Sort of. Thank you guys both very much.